I suppose, is the fact that we didn't even know that we lived in a galaxy for up until just about 100 years ago. So while it was pretty obvious we lived next to something pretty bright and easy to study, it's actually not that easy to study in the case of our star, the sun. It's actually not that easy to study the Milky Way galaxy because we can't see the forest for the trees and the dust. So we're going to come to that. It's really kind of an interesting story as to how we figured out that we do live in a galaxy. So here's what we see in the night sky. And this is the summer Milky Way. It's the brightest part of the Milky Way. And we weren't really sure what we were looking at. William Herschel, back in the 1700s, did use a telescope, and he could see that along here and here, you could see many more stars per square degree than you could see out here. And of course, that's obvious by eye as well. And he made the simple but not too unreasonable assumption that on average stars are about the same, and therefore seeing so many dim stars here, what you were really seeing is that stars that were probably something roughly like the sun, and they were just farther away. So he mapped out what he called the universe, but we now know to be the pancake-shaped thing, which is our galaxy. And then notice how along the middle here you don't see so many stars, and of course he didn't see so many stars either. He wasn't sure what to make of that, but it does show up in his early maps of what he called the universe. Now, looking out nowhere near the Milky Way in the sky, in fact you want to look at directions opposite the Milky Way, near the galactic poles, and since the 1700s, when we had telescopes good enough to see them, we saw these faint fuzzy blobs. And in fact, the better the telescopes got, the more of these fuzzy blobs we saw, to the point where, in fact, today there's more of those than there are stars. They're easier to find in terms of how many per square degree than there are actual stars. We didn't know what they were. They were dim, they were fuzzy, they were oblong. They had a central bright concentration, what we would now call a central bulge. So were they nearby solar systems, perhaps, that were still forming with the sun at the center, and that was causing the excess brightness? Or were they perhaps giant pancake systems of uncountable numbers of stars? In other words, if you take what Herschel saw and assume that it has an edge, and then go out many, many times further away than the edge, which was kind of mind-boggling back in those days. Now you're talking about millions and millions of light years. Then you could imagine that those faint fuzzy blobs could be entire systems just like our own. But it wasn't obvious what they were, and the debate over which of these two was correct kind of raged right up until the 1920s. So how did we finally figure that out? Henrietta Leavitt is key. She was an astronomer at Harvard Observatory, and she worked in their Cape Town, South Africa observatory, where there's a great view of the nearest and largest, brightest, I should say, galaxy, as we now know, in the sky. And it's called the Large Magellanic Cloud, named after Ferdinand Magellan, who first saw them, the first European to see them. Obviously, native people in the southern hemisphere had seen them for eons. Anyway, they got the name Large Magellanic Cloud, and then there's a smaller version nearby. It's called the Small Magellanic Cloud, and we'll look at those a little later in more detail and figure out how they're related. But at the time, it looked like just a giant star cluster, a superstar cluster, not a cluster of a few dozen or a few hundred stars like the open star clusters that we looked at in the previous chapter, and not even like the globular clusters that we're going to look at a little more closely in this chapter, that are 100,000 to 1,000,000 stars. This was hundreds of millions of stars, or perhaps even billions of stars. So a super star cluster, but yet bright enough and big enough that you could see individual stars. It clearly was not a nearby forming solar system like we speculated these little fuzzy balls were. And she studied it, and she found that there were stars that varied in their brightness. They got brighter and dimmer and brighter and dimmer in a very regular pattern. They're so-called pulsating variable stars, as we know now. And we named them Cepheids after the first of the well-known examples in our sky. One of the brightest is Delta Cephei. It's the fourth brightest star in the constellation Cepheus. It's a star that I have my students study. It's pretty easy to take naked eye measurements and combine them together at the end of the semester and make a light curve and see that the star rises in brightness and then falls in brightness with a period of about 5 days. So she found a lot of these type of objects. They had the right color, kind of a little bit more on the yellow side compared to the sun, and the right light curves to be classified as Cepheids. What was interesting is she found that the brighter they were, the longer they took to pulsate. And the shorter they pulsated, so just a few days perhaps, then the dimmer they were. I mean, the average brightness of them was dimmer. Now, in our own sky, we can see Cepheid variables of all different distances, and so their brightness doesn't show this correlation. The special thing about the Large Magellanic Cloud is it takes up a piece of sky that's only a couple of degrees across. And if you assume that the depth of the system is similar to its width across the sky, and that's a decent assumption, we don't live in any special place in our galaxy, so there's no reason to assume that it would be anything other than roughly the same in depth. That means that within 5% or 4% or so, these stars were all at the same distance. And that's what allowed this relationship to show up. Now, she didn't know what the absolute magnitude is. Here in this diagram, we have absolute magnitudes put in. This is an old diagram, but it's not that old, 1961. We did have things figured out reasonably well by then. But it actually took quite a while before we could really figure out what the absolute magnitude of these really was. So what she knew was that there was a correlation between their apparent brightness, the little m here, and the period that they took to pulsate. So this is log base 10, so these would be Cepheids that take 100 days to pulsate. Not very many of those. 10 days, that's a lot more common. And 3 or 4 days, that's very common. Is obeyed, and you know the period, let's say this particular Cepheid in this star cluster is exactly 10 days, then you just read off from this here that it must be 3,000 times the luminosity of the sun. Then you measure its average brightness over its cycle, and you figure out from the inverse square law of luminosity how far away it must be. Sorry, I said that backwards. We know the distance to the cluster already because we can see its main sequence, so that's main sequence fitting. And then that allows us to take the average brightness of that Cepheid and realize that, oh, that's got to be, that's 3,000 times the luminosity of the sun. So it enables us to put numbers on the left axis here. And you'd like to do that, of course, for many, many Cepheids so that you can average out over the different things that could confuse you, like maybe intermediate dust between you and the clusters that can affect the brightness. So in other words, the Cepheids make excellent distance indicators. So the next big distance indicator in the distance ladder, after parallax and after main sequence fitting for star clusters, is Cepheids. What's great about Cepheids is they happen to be among the brightest stars. We looked at them in the last chapter and we saw that they're right up at the top in the red giant area. These were along the instability strip in the HR diagram. And since they're so bright, they stand out among the other stars in the galaxy. So what you do is you take a bunch of photos and you measure the changing brightness of the stars that look like they must be Cepheids, verify from the light curve that, yep, from the color and the shape of the light curve, those have got to be Cepheids. Construct the light curve, measure the period of the pulsation, pick off the luminosity from the Cepheid period luminosity relation, and then you can calculate how far away that star must be to have the luminosity look like the apparent brightness that we see from here on Earth in our photos. So to do that correctly is a little more complex, and there's a lot more to it actually, but there's actually several types of Cepheids. There's classical Cepheids and there's type 2 Cepheids, also called W Virginis stars. Metallicity has a small effect. It's not completely negligible, and so there's some subtleties to it. But as long as you measure the brightness and luminosity in the infrared, you can beat some of these problems. Okay, so how do we know from Cepheids that our Milky Way along the sky is actually a galaxy? So it kind of happened in reverse. What we ended up doing was discovering that the nearest brightest example of a galaxy, fuzzy object, possibly, as we thought, perhaps, forming nearby star system, planetary system. But Edward Hubble in the 1920s used the new largest telescope in the world, the 100-inch Mount Wilson telescope, and he imaged the Andromeda Galaxy carefully enough that he could actually pick out the brightest individual stars in that system, and at that point it ceased to be called the Andromeda Nebula, as it had been known, as just a big blurry ball, and became the Andromeda Galaxy. So that was when we really learned that they were galaxies. So the way he did that is he found stars that looked like Cepheids, and he looked at their brightness, and he said, my God, these things are incredibly dim. These are like 20th magnitude or something. Way, 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 way dimmer than anything you'd see in our galaxy. And he realized that this system was not something a few light years or a few dozen light years away, but it was more like 500,000 light years away, or with better measurements later and a better calibration for the Cepheids, more like 2 million light years away. There's the Andromeda Galaxy. I want you to notice the stars that are out here. These are stars in our own galaxy. The Andromeda Galaxy happens to be not that far away from the plane of our own galaxy, so we see many of our own nearby stars, and even not so nearby stars, in our own galaxy. And now I actually studied the Andromeda Galaxy when I was at UCLA doing my doctoral thesis. So I had to use planetary nebulae as dynamical probes and figure out the distribution and the dynamics of the disk of this galaxy. And also this little guy here, that's actually another galaxy. That's a so-called elliptical galaxy. We'll describe those a little later in the next chapter on galaxies in general. This is also another galaxy. It's also an elliptical galaxy. These are both little companions to the big galaxy here, the Andromeda Galaxy, which otherwise is a lot like our own Milky Way. I want you to notice the center is reddish and the disk is more bluish. And so what that's telling us is that the bluish part, the bluish stars out here, these are dominated by the light of blue giants, massive stars that are in spiral arms. See these spiral arms here. These are telling us that these are places of recent star formation. Recent star formation can include stars that are very high mass, even though they don't last very long, and they're among the most luminous of stars. The center of the galaxy is dominated by red light because star formation down here was shut off long ago, and so this is an old stellar population and dominated by the light of red giants. But we'll come back to that later when we talk about stellar populations. Okay, so you can map out, looking at Andromeda now and realizing from the Cepheids that this is actually a separate galaxy. and look at the structure of it. And so here's the basic components. There's a spherical component, sometimes called the halo out here. And then the inner halo is actually called the central bulge. Here's where the stellar density is high enough that you can literally see it as a blur of stars. Then there's individual bright clumps, which if you look at carefully you can see are actually clumps of 100,000 to 1,000,000 stars. So these are the globular clusters. There's globular clusters in our own galaxy as well, and there's globular clusters in Andromeda. And not surprisingly, their distribution is centered on the center of the galaxy as a whole. And there's fewer of them as you go out, and more of them and denser as you go in. Then there's the so-called disk, and the disk is here. That's the bluish part. And then in the center, in a vertical sense, of the disk is the reddish stuff here, and what that is interstellar gas and dust, which settles into a finer and thinner plane than does the stars, which occupy a more inflated, a thicker disk. Okay, and then there's also stars out in the halo here that are not members of globular clusters. The globular clusters are the easiest things to spot because they're just so bright. But if you're careful and you look carefully, then you can actually see individual stars out here. It's just pretty sparse. So where are we in this huge system that we call the Milky Way? Again, it's not so easy to tell because, you know, we're in the middle of it. And we're seeing it edge on. And all the dust is in our line of sight as we try and look towards the center and look towards the edge. And so we were fooled by the fact that when we look at other galaxies, we see this bright, star-like almost, well, not really star-like, this bright, dense ball of stars that's so dense it is clearly the brightest part. In fact, if you look up in Andromeda with your naked eye in the fall, you'll see a big fuzzy star, and what that really is not a fuzzy star, it's the Andromeda galaxy. And it's the collected light of maybe 100 billion stars, all in the central bulge. It's so clearly the brightest part of the galaxy, and since we don't see anything like that in our night sky, we thought that, well, maybe we actually live in the center. So in the early 20th century, we didn't appreciate the dust that hides our view, and we actually thought that we might live in the center of our galaxy. Here's globular clusters, though. These are the ones that are going to tell us where we really live. You can just tell, looking even at this photo, that these things are ancient. The brightest stars in the globular are the red giants, like that guy and that guy and that guy. This blue star here, he's a foreground star. He's not a member of that cluster. And the hotter stars, the whiter stars, are all much dimmer. So this is telling you that the main sequence turnoff point is far down into the area where the sun is, not up in the area where the blue, more massive stars are. Those massive stars have all died already, and it's only stars that are about the mass of the sun that are still on the main sequence, and even those are starting to turn off and become red giants. So when you look at them more accurately, then you can tell with your stellar models that, yeah, these globular clusters are about 13 billion years old. 12.5 to 13.5 billion years is the age that you get when you look at these. You can tell in this photo, as a comparison, you can see how much more massive a globular is than the Pleiades, which is a open star cluster. This is the brightest open cluster in our sky. It's not a particularly rich open cluster, but it's the nearest. One of the nearest. So let's look at some more globulars up close, and you can see it gets pretty darn crowded down here. In fact, we can tell you now that in the last in the last decade or so, we've got good enough technology to tell that we have black holes of roughly 1,000 solar masses that have been built up in the action of the formation of these globular clusters. There's another one. This is one of the richest ones. This is Omega Centauri. And this weird pattern here is actually a whole bunch of photos from the Hubble Space Telescope that, and then this is just a rather overcrowded picture from the ground, overexposed. But we can zoom in here and see it up close, and it's just mind-boggling how many stars there are. And also it is just so obvious that it's the red giants whose light dominates these clusters. So these globular clusters look kind of orangish reddish. And the main sequence stars, these are stars that are only about as massive as the sun or a little less. Lots of those too. So here's the thing. Hubble found globular clusters in Andromeda as well. And they're roughly spherically distributed and centered on the center of the galaxy. But we had known in our own sky since the days of William Herschel, who mapped out where the globular clusters were in our night sky. And any star chart and any amateur astronomer will tell you that globular clusters strongly concentrated in the summer sky and strongly concentrated in the constellations of Scorpio, Sagittarius, Ophiuchus, Centaurus. Those are the constellations that are closest to the center of the brightest part of our Milky Way as it bands the whole sky. That must be the center. So that was the clue. The center of our galaxy is not where we are. It's off in the direction of Scorpio, Sagittarius. Can't get damped out for stars. Vertical motion can get damped out for gas and dust, but not for stars. They're too dense, and they just don't feel any air friction with the very, very low density interstellar medium.